Hello everyone, welcome to this next video on previous year's questions of integral equations. This question is from June 2019 consisting of 3 marks. The question is, if y is a solution of this integral equation, where what is this? Y of x minus integration from 0 to x minus t yt dt is equal to 1, then which of the following is true? They are asking whether y is bounded but it is not periodic. Y is periodic in R, this integration is finite and this integration is finite. So which among these 4 is valid for the solution y of the given differential integral equation, right? So for that, what we have to do, we have to solve this integral equation. One way to do this is you just convert this into a differential equation, right? Convert this into ordinary differential equation. The second way is that this is a Volterra kind of equation. The second way is that you use Laplace transform to solve this. Why we can use the second approach? Because here the kernel given xt, that is given to be x minus t, which is of the convolution form, and we know when we have this convolution form, there is a result in Laplace transform known as second shifting theorem, which gives us ease to solve kernels of this kind, equations with kernels of this kind, right? So let us proceed. So we are given y of x minus integration from 0 to x minus t yt dt is equal to 1, right? Now let us take the Laplace transform. If I am considering my domain is in the variable x and my range that is in the variable s, right? And I am applying the operator L, that is Laplace transform from this domain to this domain. Then if I apply, first of all, let me write this as convolution, this thing in terms of convolution, right? So it would be minus and it would be x star y of x is equal to 1. Where what is this star? Again, this star is the convolution operator, right? And what is the definition for that? I've already told this in the previous videos, but for the sake of completeness, let's have a look. Any function f of x convoluted with another function g of x, that would simply be equal to integration from 0 to x f of t, first function as it is, right? But the variable is now changed from x to t, multiplied by g of this x minus t dt, right? So this is equal to this thing by definition. So our equation becomes this kind. So we can now apply Laplace transform on both sides. So let us do that. So it would be Laplace transform of y of x minus the Laplace transform of x star y of x is equal to Laplace transform of 1. Now here you should know some formulas of Laplace transform. These are the very basic formulas. If I am calling the Laplace transform of y of x is equal to capital Y of s, right? This is the notation. So I can replace this term with capital Y of s, right, to denote its Laplace transform, which is unknown at this point of time, and we have to solve for this. Minus, here you should know that Laplace transform of some function f of x convolved with another function g of x, that is equal to the Laplace transform of the first function multiplied by the Laplace transform of the second function, right? So the convolution after taking Laplace, it simply reduces to multiplication of the Laplace transforms. So this becomes the Laplace transform of x multiplied by the Laplace transform of y of x, right? And what was that? It was equal to capital Y of s. And the Laplace transform of 1, that is simply equal to 1 upon s. So this is the formula, right? So this is equal to 1 upon s. And what is the Laplace transform of x? We know the Laplace transform of x raised to power n, that is simply equal to n factorial divided by s raised to power n plus 1. So it would be equal to 1 upon s square, right? So we have this term, we can take y of s common, so we'll have s square minus 1 divided by s square, that is equal to 1 upon s. So ultimately what is y of s? That would be s divided by s square minus 1. Now we obtain this term. Now what is left? We are to take Laplace inverse on both sides, because now we have to move from Laplace domain to the original domain, right? So now this is the S domain and we are applying Laplace inverse on both sides to obtain again in the X domain, so that we can find our solution in this domain, right? So taking Laplace inverse on both sides, what would we get? Laplace inverse of y of s, that would be equal to Laplace inverse of s upon s square minus 1. Right? So this would simply be y of x, and what would be that? And here again we are using the formula Laplace inverse of s upon s square minus alpha square, that is simply equal to cos hyperbolic alpha x, right? In this case this alpha is simply 1, so it would be cos hyperbolic x. So this is our solution. So cos hyperbolic x is our solution. Now in the question, what are they asking? They are asking whether this y is bounded and is not periodic. Let us see. We all know what is the graph for this cos hyperbolic x. It is of this kind, right? So, and passing through a region, by the way. So clearly this is not bounded, right? So this is not bounded, so this option is discarded. Is it periodic? Can you see any period or any interval after which this function is repeating? No, we cannot. Therefore, this function is also not periodic. So this option is also incorrect. Let us see the third option. What is that? Integration over the region R, y of x dx. This is the integration we have to perform. So let us do that. Integration over the region R, y of x dx. And what is our y of x? It is equal to cos hyperbolic x dx, and the integration of cos hyperbolic dx, that simply is sine hyperbolic x, limits from over the region R, that means limits varying from minus infinity to infinity. That is surely not finite, that is surely infinite, because we are talking about this function, or we are talking about this function when the area between this function, right? So this is not finite, so this option is also incorrect. Moreover, we have to check the fourth option, although this should be correct because all three are wrong, but for the sake of completeness, let us just do it. So the fourth option, that is integration over the region R dx divided by y of x, right? So moreover, you can write cos hyperbolic x as e to the power x plus e to the power minus x divided by 2. We know this is the definition of cos hyperbolic x, so it would be integration over the region R into 2 dx divided by e to the power x plus e to the power minus x, which would simply become 2 e to the power x dx divided by e to the power 2x plus 1, right? So now we can substitute here. We can put e to the power x as some other variable z, so that e to the power x dx would become dz, and so this term would become integration. Now the limits also change. Earlier the limits were from minus infinity to infinity. Now the limits becomes start from 0 and end at infinity. You can check that. So it would be 2 dz divided by z square plus 1. So that would be, what is the integration? This 2 would be is constant, comes out from the integration side. The integration of 1 by z square plus 1, what would be that? Tan inverse of z, and limits from 0 to infinity. So that would be pi, and this is surely less than infinity. So this option is correct. So we have option 4 as the correct option to this solution, right? That is it for this video. Thank you for watching.